Hi there, grade 12s. I'm back again with you for Physical Sciences grade 12. And my name, as you know, Tinyiko Kosa. You're welcome. Please, let's go through this lesson together. I hope you're going to learn a lot from it. Now, today we're going to talk about section on waves, and that topic is found under waves, light and sound as our knowledge area. Now, let's come to the lesson itself. Waves, sound and light is our knowledge area, and we're going to look at 2D and 3D wave fronts. Now, like that part there already says, we will be talking to wave fronts, we will be talking about Wavelength's principle, we will be talking about diffraction, we'll be talking about interference. Now, all this is around waves, okay? So when we talk waves, we can't talk waves without talking this kind of sections or topics. We know that waves will have wave fronts. We know this gentleman here is one scientist that studied quite a lot around waves, and he's got a lot to say about it, as we're going to see as the lesson unfolds. And diffraction is one of the properties of waves, that waves undergo diffraction, and also interference, that waves do interfere, and we will be talking more about what happens when waves interfere. Right. Now, let's look at wave fronts. What is a wave front? A wave front is a series, maybe let's just start by just defining what a wave is before we come to the wave front. A wave is a series of regular, repetitive disturbances or vibrations in a medium. So the medium could be air, it could be some solid medium, it could be any other medium, water. So that is caused by a vibrating source. So there must be a source that creates or generates those waves. Now, a water wave, for example, when we view it from the side, now you're standing just next to the sea, you are just on maybe at the beach, right? And you're looking at the sea and you're seeing these water waves. When you view these waves from the side, what you see is a two-dimensional view. In other words, you've got the Y and the X. Now, you've got the Y view and the X view. That is two-dimensional. Now, when you look at this wave in a two-dimensional version, what you will see is those type of, or that type of shape. That's what you will see, okay? Having the height and that length there by the bottom. But if you are to look at this wave and you are looking at it not from the side, but you're looking at it in such a way that you are able to see the 3D version of the wave. So we're now talking the three-dimensional view of the wave. What you will have is now both the Y and the X as we started. But then added to this, you will also see the Z, the third dimension of the wave. Now let's look at it carefully and see what we're talking about here. It means you will see the bottom part of the wave that way, it means you will also see how high the wave is. You will also see this part of the wave, which is given by the z-axis. And we mean look at that top there. You are able to see that top of the wave, the side of the wave, and you're also seeing the height of the wave. Now, when you look at the height of the wave, if this bluish curved line there represents one particular wave, and that darker part there also shows another one, you would say maybe you're looking at some two waves there in a three-dimensional way. But then what I want you to see here is, if this whole thing is just one wave, you will see that there is this point here, there is that point, and that point, even the very last one there. Those points there are in line with each other. That means that when this wave motion has passed that point and it's somewhere here, for example, these points will still be at some linear form like that. Even when we look at them at another position somewhere there, these lines or these points will still be lined up in that way. So in that way, we say that these points of the wave are in phase. So these points are in phase. Now we'll talk more about what we mean by waves being in phase, or points in a wave being in phase as we move on. And it is very important to understand that, because that will make us understand easier the issue of interference, how it happens, and why the kind of interference happening there. And even the diffraction itself, we need to talk about these points on a wave being in phase. Now, when we look at these points that are in phase, what does it result in? Now, remember, we're speaking about wave fronts. And we are saying that a wave front is an imaginary line that connects adjacent points in a medium that are in phase with each other. In phase with each other, like I've illustrated earlier on, is that these points are moving in a similar position throughout the wave motion. You can't find one remaining here, the other one there, the other one there, and at some point they come together. They move at the same time, they move together, and therefore even their speed is the same throughout that wave motion. Okay, so when these points are put together, the points that I was showing perhaps in the previous diagram, when those points are put together in that way, those points, a line drawn to connect them, will be called a wave front. So a wave front is an imaginary line that connects adjacent points in a medium that are in phase with each other. So that will be a wave front. Now, from the points I drew earlier on, if you say, for example, you have got this situation here, where those points I drew earlier on actually are forming that line. So they are in phase. And we call this, like we're saying, a wave front. We call it a wave front. So in similar way, this line here, which is a wave front, is connecting points on a wave that are in phase. They can form that straight line. Now that straight line is imaginary, like we say. It's an imaginary line connecting points that are in phase in a wave, and we call that a wave front. So here we'll be having 1, 2, 3, 4 wave fronts. Right. Now this will be the top view of what we started with. If those lines are drawn for this wave here, okay? If we look at this wave from the top, from this side, those are the lines that we're going to see if we look from the top. So the top view of that wave will show us this, which is our wave fronts. Now let's look at something that we can refer to from a ripple tank. We know that this is what we can use in our own laboratories to generate waves and check what is happening. If you have got a ripple tank and waves are generated on the water inside the ripple tank, what you will see is that you will have lines or waves where you will have the top sections going up there, and you will also have something deepening down there, which will be this line here. Okay? So in that way, you will be having what we call this top here will be giving you what we call the crest of the wave. And this part here will be giving you what we call the trough of the wave. Okay? Right, so that's what you will see. And then these lines here will be representing your wave front. Why will this be representing your wave front? Because this line here is drawn along all the points that are in phase on this wave. Now those will be lines that are in phase, and then a line drawn through them, straight line like that, gives us what we call a wave front. Now, this means that we can't have a point there on this wave, and a point here on that wave, point there, point there, point there, and join them and say we have got a wave front. It's not possible because all these points here are not in phase. And when they are not in phase, we say they are out of phase. And they are not of much use to us because we look mainly to those that are in phase, because those that are in phase will give us our wave front. Only points on a wave that are in phase are going to give us our imaginary line called the wave front. Okay, now that's what we need as sort of foundation, sort of something that we need to keep referring to as we move on with this lesson, and also in answering some of the questions we need to refer back to this knowledge that wave fronts are actually an imaginary line drawn to connect all the points on a wave that are in phase. Okay, now let's move on. Let's come to talk about properties of waves. Now, we need to know that waves travel in straight lines. They don't bend around. Once they start traveling in a medium, if a wave is traveling in a medium, it will travel in a straight line. It will not curve and move about, things like that. It will travel in a straight line unless something happens to it. Unless it is disturbed on its path, then something may happen. But if you allow it to move freely in that medium, be it water, be it air, that wave will move in a straight line. That's one of the properties of waves. They move in straight lines. But like I said, if you introduce something on the path of a wave, you are disturbing it, okay? And something will happen. But when they move out from that source, they will travel in straight line. Another property of waves is that waves undergo reflection, Quickly, we're not going to dwell much into this, but we need to know what is reflection. You see, reflection is when waves will be bumping against an obstacle and they come back along the same path but in opposite direction. That will be reflection. So the waves comes back along the same path in opposite direction. And then we also have this property here called refraction. So waves can be refracted. What do we mean by this? Waves can be made to change direction as they move from one medium to another. Now, when waves move from one medium to another, for example, when light moves from air into an optical object, okay? There will be refraction there because the optical object is denser than air. So, in moving from less dense to more dense objects, waves are going to be refracted. That is the change in direction of the waves as they move from less dense objects or medium to more dense medium, or vice versa. So as long as the medium in which they are moving changes its density, you're moving from one medium of a different density to the next one, that refraction is bound to happen. So waves will change direction there. Now, the third one that we need to know about waves as a property of waves is that waves undergo interference. Now, what is interference? Interference is when waves come together. They're either going to have what we call constructive interference or destructive interference. And that process there, or that particular phenomenon, is known as superposition of waves. So you've got waves coming together. Okay? They are either going to reinforce each other or cancel out or minimize each other, whatever the case may be. And we're going to look more into it later on in this lesson. We're going to learn more about interference. Right, so those are the three very important properties of waves. And we need to know that because we need to refer back to it most of the time as we learn other things around waves. Let's talk about now the principle of superposition. I've touched on it a little bit. Now, the principle of superposition, we look at it, or it happens when we talk interference of waves, like I said, thus. When we talk interference of waves, this phenomenon, or this principle comes in. Call it the principle of superposition. What happens here? Here it's waves merging, coming together into each other's paths, and what happens there is that you can either have the waves resulting in what we call constructive interference. And the word constructive can say more on its own. Constructive interference might be saying to you, or it's saying to you, that there is reinforcement here. In other words, what you started with, reinforcement. What you started with is made larger than before. Larger than before. Okay? And I'm going to take an illustration later on. But just to quickly explain to you, say, for example, you've got a wave, or let's say a pulse, single disturbance, and that is a trough of it, and it's moving in that direction. And you have another one, say just that small, moving in this direction. These two pulses are going to meet somewhere here. When they meet, what is going to be the result here is that the two are going to reinforce each other, leading into constructive interference, where instead of just having this amplitude, so that's the amplitude, from the rest position of the wave to that point is the amplitude A of the wave. Now, if this amplitude here, say it is 2 centimeters for argument's sake, and that amplitude there, okay, for this one is 1 centimeter. 1 centimeter. When the two meet here, they will reinforce each other such that the resulting trough will have an amplitude of 3 centimeters. So this would be constructive interference. Now, so in short, that is what we're having in terms of constructive interference. But at the same time, we can have what we call destructive interference. Now, what happens with destructive interference? Let me have a bit more space here. Now, the word itself suggests to us what is going to happen. We expect these reinforcement not to happen. It is gonna lessen, and I'm going to use a simple one where it cancels out completely. This time, say we have a pulse moving in that direction. And this side, we have another pulse, but the crest in this time, not the trough, so in that direction, in that way. And it is moving in the opposite direction. And say the amplitude of this one, A, is 2 centimeters. And the amplitude of this one is also 2 centimeters. When the two meet somewhere here, remember there is a question of direction here. This one going up, let's say it's negative. And this one downwards, it's positive. When we add the two together, we're going to have a cancellation. So the addition of the two will be plus 2 centimeters plus minus 2 centimeters. Now, what will result here is 2 minus 2 centimeters, which is 0 centimeters. So there is a cancellation here. Therefore, there is destructive interference. So when they meet somewhere here, that's what is going to happen. This is going to cancel out completely. And that type of cancellation is going to be it's known as destructive interference. These waves are interfering with each other, but then they interfere destructively. They give you 0 amplitude, nothing of reinforcement. Destructive interference occurs, as opposed from the previous one where we looked at when the two are in opposing direction, they meet each other in opposing direction in terms of the crest and trough. So you have got the trough and the trough meeting, not opposing, in the same direction, and then they are moving in opposite direction, meeting each other somewhere, and at that point where they meet, they are going to have a positive reinforcement, which is called constructive interference. Now, that is very important because what we will be talking more about in terms of the Huygens principle, we'll be touching a lot on interference. And we need to understand these basics here to be able to understand what Huygens is actually talking about. So let's move on and have a look at the next section of the lesson. Let's look at this one. And we're calling it example 1. Now it is on interference. We have got 2 wave pulses. The first one is A, the second pulse is B. A is moving in the direction right, so it's moving in that direction there as shown, and B is moving in the direction left, in that direction. We have got an amplitude of A there being 2, let's call it 2 centimeters for argument's sake. and the amplitude of B is 1 centimeter. They are both pulses of two waves. Now, they are, because they are moving in opposing direction, somewhere they are going to meet. At some point, they are going to meet. So say they meet at that point there. If they meet at that point, what are we expecting to happen? Because these are pulses, you know, the same orientation, they are all both in the upwards disturbance, if you like. It means when they meet here, they are going to reinforce each other. And when they reinforce each other, say the top direction, we call it plus. So it will be plus 2 centimeters, like we said. We add the other one. It's also plus in the plus direction, but this is 1 centimeter. So what we have at the end is 2 centimeters plus 1 centimeter, and that will be 3 centimeters. So we have had a reinforcement, and therefore we have an increase in the amplitude of the two as they meet each other at that point. Okay, so at that point the amplitude of the disturbance will be 3 centimeters. But there's something that I want to quickly explain as well here, because we cannot say that, okay, they reinforce each other and it ends there. But what happens actually is that as the two separate after meeting here and having that huge disturbance, if you like, of 3 centimeters, okay, 3 centimeter amplitude. When they pass each other, this one continues in that direction as, again, just 1 centimeter. This one will also, after that incident there of them interfering with each other, it will continue that side in that direction, and then it will also go back to its initial amplitude of 2 centimeters. So that is also important, that what we're talking about is the superimposing the two waves together at that point happens at that point, and as the waves separate and move further in their motion, then they regain their size in terms of the crests and troughs, whatever the case may be. In terms of their amplitude, they regain that size. So we need to understand that. Now let's come down to this one and say, sketch what will happen when they interfere. Now, let's quickly, like I've shown there, actually that's what is going to happen, but let me just rework this out again as a way of reinforcing it to you, and you getting clear picture of what is happening. What is going to happen here is that this one, let's just look at the point where they meet only. So you've got B being the smaller one there, and you've got A being the bigger one. They are both meeting there, and then that's what you're having at that point. Sorry, this should be together. They should be meeting there. Okay, and what is going to happen is that this one will not, these two are going to superimpose, to get superimposed into each other, and what will be the resulting pulse will be the sum of the two. So that will be the resulting pulse. So if you check the resulting pulse, it will be this one, which was 1 centimeter amplitude. It will be the other one with 2 centimeters of amplitude. Okay, I think this should have come up there. And then together they give you the 3. So let me just draw this one from here right up to there. And this is now 3 centimeters, if you like. So this is what happens at that point where they meet. But then, like I explained earlier, remember that this brown one is moving in that direction. So after meeting here, the brown one will continue in its direction and regain its size in terms of amplitude. It will go back to 1 centimeters. This one, on the other hand, the blue one, the bigger one, will also continue because it's moving in that direction. It will also continue, regain its amplitude of 2 centimeters and proceed in its direction. So this superposition there, which happened due to the interference of the two, occurs there and then at that very point and not anywhere else. When they separate, they move on in that direction with their initial amplitudes. That is very important to note. Right, now, let's move on now and begin to talk about Huygens principle. Now, like I said, we will be referring back to interference a lot when we are to understand Huygens principle. We will be referring back to the points on a wave that are in phase, okay? So we'll be talking about the wave fronts, imaginary lines joining points on a wave that are in phase. So all this is necessary for us to understand Huygens principle better. Let's come to it. Huygens principle. Now let's hear what Huygens is saying here. Huygens is saying that each point on a wave front acts as a source of spherical wavelets that spread throughout the medium. Now, what does this mean? If we have wave fronts, like we said, so we have wave fronts like this. These are lines joining points on a wave that are in phase. If we have fronts like that, Huygens is saying that each point on a wave front, if I look at this point here, that point, according to Huygens, is saying it is acting as a source, so it is generating smaller waves, wavelets, that are spherical. So we have got waves happening in that way for every point on the wave front. Now, the same thing is happening. So we've got multitudes of points on these wave fronts here, and all of them are acting as sources of waves. So that is what he is saying. And we need to look at the consequences of what he is saying and in terms of how waves behave. Let's now come to the key points on Huygens principle. Now, the key points that Huygens is actually putting forward is that, firstly, like I've just explained, each point on a wave front acts as a point source. And this point source generates waves that travel spherically in all directions. Now, that's very important. If you look at my drawings up there, I've tried to show it. Okay, so every point I'll look at on a wave front will be regarded as a source, okay, of secondary waves, and those waves are spherical waves that are generated and spread outwards in a spherical form like that. So that's what happens. So that happens as they generate, as the waves are generated from the point source, they move in all directions in a spherical way. Similar to circular waves caused by dropping a small stone in a pool. So that's what Huygens is saying. Right, the sum of the wavelets, the sum of the wavelets from all the point sources produce the next wave front. Okay, So if you add all the the disturbances there, okay, wavelets from all the points, if you add them, that then becomes the next wave front. This was the previous wave front, and there would have been the next wave front here from this one. So that's what he's saying. In other words, it's explaining the behavior of waves using a different approach, and that's what Huygens brought up. And it's a very useful explanation of what happens actually as we look at waves and how do we come to have those wave fronts and points being in phase. So let's just move on and have a look at this diagram here. Now, this illustrates further what Huygens is saying. If we take these points here as wave fronts, okay, so these are wave fronts. Not these points, but these lines as wave fronts. Now, let's look at this one here. On this wave front here, from bottom upwards, we can look at points on the wave front. And these points here, according to Huygens, act as secondary sources of wavelets. And they generate those waves, and look at how the waves move. The waves move in a circular form. And what Huygens is saying is that all points that are in phase on the secondary wavelets form another wave front. So that will be another wave front according to Huygens. So that is what is happening. Even here we can do the same. We can have points that are in phase on the secondary wavelets, circular ones, and if we join all of them together in a straight line, of course, that will give us another wave front. So that's what he's talking about, and very, very understandable. Of course, it's. I think the theory is marvelous. I love it. It actually says a lot about waves and opens up a lot of understanding in terms of how waves behave. Right. Now, let's look at diffraction. Now, diffraction. What is diffraction? Diffraction involves bending of waves, and it's actually the wave fronts as they bend. What happens for them to bend? They bend because they are now passing around a straight barrier, or sometimes it's because they are passing through slits. It could be single, it could be double. So diffraction involves the bending of waves as they experience barriers in their motion, as they experience objects that actually stand on their way. Okay, now, so that will be diffraction, bending of waves as they encounter obstacles or barriers. Now, let's look at this now. The diffraction patterns. What happens when the waves pass through a slit? Perhaps going backwards, if we've got waves here meeting, here are wave fronts, and all of a sudden they meet an obstacle. Okay, say the obstacle is here. Something is placed on the path of the wave. What is going to happen as the wave pass through this? Okay, so you will have that. Remember, waves move in straight line. But these ones, okay, here, what is going to happen is that these ones would be wanting to bend around that obstacle in that way. So you've got that situation that these waves here that has been disturbed, or these wave fronts that have been disturbed here, are continuing. And remember, according to Huygens, that point there becomes a point source. And that point source begins to create circular wave fronts there like that. So that is why they are able to bend around obstacles, because every point on a wave front is regarded as a secondary wave source. And in that way, we have waves bending around obstacles. Now, let's look from these diagrams here what happens if we have got slits. Now, here we want to check what happens when we have got the slit of the size of the slit changing. Here we have got a much bigger size of the slit, and the slit size is denoted by small letter a. So this is a bigger size of the slit compared to that one, which we will be touching on later on. Let's concentrate on this one. Now, look at it. The disturbance here due to that slit has caused that spherical waves to be formed in that way. But then if we compare it to the amount of diffraction, look at that, this is less diffraction compared to that. If we have a smaller slit, the diffraction seems to be bigger. In other words, the bending of waves is bigger compared to when we have a bigger slit, a big size, okay? The size of the slit is bigger here, and it is less there. Now, what does it tell us about the relationship between the slit and the amount of diffraction? It tells us that the size of the slit tells us that the size of the slit is, or let me just put it this way, has an effect on the amount of diffraction. So size of the slit determines the amount of diffraction, how much diffraction we can have. And we can actually see the relationship between the two. We can see that the diffraction is more when we have a smaller slit, and it's less when we have a bigger slit. So we can say that the bigger the slit, the smaller the diffraction. So we can say that diffraction is inversely proportional to the size of the slit. Diffraction is inversely proportional to the size of the slit. So this tells us that the bigger the slit, the smaller the amount of diffraction, as shown in our two diagrams here. But then, something that I may not quickly show to you, but please understand this. The wavelength of the wave also determines, or it is a factor that also plays a role in determining the amount of diffraction that would happen to a wave. Now, how does this wavelength affect the amount of diffraction? Now, here we have a situation where diffraction is directly proportional to the wavelength. So diffraction is directly proportional to the wavelength. to the, to the wavelength now. So diffraction is directly, sorry about this, is directly proportional. Directly proportional to the wavelength. Now, what does this mean? It means that as the wavelength increases, the more we would have the amount, the diffraction. So diffraction increases with wavelength. If the wavelength becomes less, the amount of diffraction will also become less. Now, in terms of mathematical representation of this, we can say, all right, we said that the size of the slit is represented by A. So if I use this part of the my screen here to summarize what we have just seen, we can say that A is inversely proportional to diffraction. And diffraction is actually represented by the angle, how much inclined the angle is in terms of, because the angle will tell us whether we have got more smaller angle or bigger angle, and that angle tells us about the amount of diffraction. So we make use of the angle there, theta, to see how the amount of diffraction is formed. Now, so A, the size, is inversely proportional to the amount of diffraction that we have. On the other hand, we are also finding out that the wavelength, lambda, is directly proportional to the amount of diffraction, which will be given by the sine of the angle. Now, in this case, if we were to put these two together, right, we can see that if we cross multiply here, from the first one, we can see that the sine of theta is proportional to A, it's proportional to 1 over A. That's what we have from this one here. Then if we put these two together, it will mean that the amount of diffraction which is given by sine theta will be proportional to, we put these two together now, so it will be lambda divided by A, which is the size of the slit. Now, to remove the proportionality sign, we know we have to bring in a constant. And that constant happens to be m. But this m, like I'm going to show again as we move on, it represents the number or position of the, it could be this time, let's just say the dark or the dark band, which will be representing the point where destructive interference occurred if we're looking at light. And of course, we can use this to look at where do we have the bright band. Now, that M, we know it can be either at position the first one or the second one or the third one. All right? Now, if it's the first one, M will be 1. So if we put M there to remove the proportionality sign, that will be M lambda over A, like I said, where M is either 1, 2, or 3. But remember, these positions can be below the angle, the horizontal line that gives us the angle, or above it. I will talk to this more in one of the sections as we move on in this lesson. And we'll see that it will either be in the positive section or part of our graph or position of dark bands and bright bands, or in the negative. So we will be saying either the plus or the minus of it. Okay, now we'll talk more about this. There's nothing to worry about at this point, but we are going to use this to understand what we'll be talking about later on as we begin to calculate for this. So what is most important here is that we have diffraction being directly proportional to the wavelength, which is that, okay, which is this one here. Okay, we have the size of the slit inversely proportional to wavelength, which is that, and when we put that together, we come to this, and when we put in our constant that will multiply here to remove the proportionality sign, we have sine theta equals m lambda over a. Now this is the formula that you are going to use more often to solve problems under waves involving Huygens principle. All right, and I think in your books, in your textbooks, question papers, you must have seen that particular formula. Right, let's move on. Now, let's look at this. Does light behave like a wave? This is a huge question. Now, for us to say that light do behave like a wave, we must have certain properties that light is displaying that tells us that this particular physical phenomenon or quantity is actually displaying some wave properties. If it is displaying those wave properties, then we can say, yes, light has a wave nature. Now, how do we arrive at that? Let's look at this. If we have got light and we're shining light in that direction here, let me have something lighter for you to see what I'm talking about. So this light is shown from this side, and let's say this light is forming these wave fronts here. These are wave fronts, these white lines. When this wave fronts reaches, or these wave fronts reach that slit, every point, we know according to Huygens principle that every point along that wave front acts as a secondary source of wavelets. Those secondary sources are going to create waves such that we're going to have some waves, spherical waves created here. So we're going to have things like this happening from each wavelet. Okay? I don't want to draw more on that. But as that happens, these secondary wavelets are going to have points where they interfere constructively and points where they will interfere destructively. Where they will be interfering destructively, if this is light, we expect to see a dark band because that will be destructive interference. So if that is destructive interference, it means the light does not exist there. We should see a dark band. But there will be points like that one where the interference is going to be constructive. So most of them will be in that way constructive, and we end up, let me just put it this way, we end up having something like that on the screen. So that line there will be joining those points where constructive interference is happening, and because this will be light, we would say that we are having a brighter band. So that will be a bright band somewhere. Yes, and that will be when we are having constructive interference. Now we're seeing this happening with light when we perform experiments. And because now there is interference that results in constructive and destructive interferences, we can say that yes, light is displaying some wave nature here, because it's only wave that can do this type of thing, interference, interfering constructively or destructively. Another thing that we are seeing is that these waves are bending around the obstacles. And in bending around obstacles, we know that bending around obstacles of waves is called diffraction. Now, this is one other property of waves. Now, if light undergoes diffraction, it will mean that light has a wave nature. So we can also say that light has a wave nature. Why? Because it is undergoing diffraction, bending of waves around obstacle. Secondly, it is undergoing interference, where we're seeing constructive interference and destructive interference. So, and those are resulting in what we see here. Suppose that this light, as it is shown onto this obstacle here with that slit. Suppose we have got a screen somewhere. Just to check what happens when this light passes through this slit. So as the light passes through that slit, what happens beyond it? So we put that screen here to see what happens. And when we check on the screen, we see that there are those points, this point here, that purple point. It shows us that there has been some constructive interference, although the band there is not that bright. It's a bright band, but not that bright as compared to this one. Here we are also having some interference, and it results in that bright band there. In between this bright band and that bright band is that black band there. That black band will be our dark band. It will be this one here that I've written. So I have written that dark band there. So that will be as a result of destructive interference. The same thing would hold for that point there, where we have got, again, a dark band. It's a result of destructive interference. But look at that central one. That's our central bright band. And in our central bright band, we've got the central bright band as the brightest of them all. That means that we have got bigger crests meeting there together and reinforcing each other more, and we have got a much brighter band there. So that's the central band for a single slit. And we have that kind of interference, constructive interference there, leading on to that bright band at the center. The same thing like here happens here, where we have a dark band. There has been a destructive interference, destructive interference. Constructive interference there, constructive interference there. And that is what's happening. So from this experimental result, we can say that light displays a wave nature as well. Okay, and we'll see, like I said in some of the lessons earlier, that light do have a particle nature, and we'll look at the dual nature of light later on. And for now, we have just proven that there is also a wave nature in light. As we see how light behaves, it behaves exactly how waves will behave when it meets obstacles. There is bending of light, so if it bends, it means it has got wave nature. And we are also seeing that apart from bending, which is diffraction, light is also interfering with each other. There is interference happening, constructive and destructive interference, and that tells us that light has a wave nature. Now let's summarize what we have just done quickly into this diagram here. Now what we have seen happening is that we had points where we had dark points, and these dark points, we refer them to as dark bands, and that is where destructive interference happened. And the purple section, that section there, told us or showed us about constructive interference. Okay, so that is the constructive interference that happened there. This one, destructive interference, the dark bands. And we also realized that in the middle here, we had the largest dark band, okay? And from that region of the largest dark band, bright band, sorry, we also realized that it was the one right at the center of the slit. There is our slit, so right at the center of the slit, our screen tells us that we're going to have the brightest and the longest band. Now, these dark bands, if I were to find out where they are, all right, let me just draw those lines there to show where they are. If I were to find out where they are, I would say we count now from the central band. The central band becomes our 0 point. And this one becomes the positive 1. So going up, that's our first dark band. We'll call it our 1, our plus 1. This one will be our plus 2. If we had another one there, we would call it plus 3 and so forth. We would call it plus 3 and so forth. In the same way, down here, this one is the first one below the central bright band. That's our first dark point or dark band, and we call it our minus 1. This is where the minus and the pluses come from, the ones I referred to earlier on. And this one is the second one down below, and therefore we'll call it minus 2. If we had the third one, like I said, it was going to be minus 3, and so forth and so forth. So that's where the minus 1, minus 2, or plus 1, plus 2 come from. Remember, this, it's something we have to use when we use that formula there to calculate the amount of diffraction in terms of the angle. That says m lambda over a. Now, this minus 1, minus 2, plus 1, plus 2 is the value of m. So we say where m equals plus minus 1, plus minus 2, plus minus 3, and so forth and so on. Right, so that's how we come to that. Now let's look now at the equation for calculating diffraction patterns, and already I have introduced to you that formula, and I have explained where m comes from, and from there we can use this to calculate or solve problems related to diffraction. We need to note that a is the distance of the slit or the size of the slit, and this must be in meters. So if we are given in millimeters, we must convert. And theta is the angle, and lambda is the wavelength, as we know, in meters as well, and m is the band number, like I've explained. Now let's look at some example quickly. Laser light shines through a single slit that has a width of 2 micrometers. The first dark band appears at an angle of 15 degrees. What is the wavelength of the light? So we can write down what is given to us. We are told that the size of the slit, we use A for the size of the slit, is 2 micrometers. And what is 2 micrometers? You must convert to work in meters, micro to the power 6 meters. We have converted now. Then we are told that the angle is 15 degrees. What we need to find out or to calculate for is the wavelength. Now, how do we do that? We go back to the formula that is given to us. Sine theta equals m lambda over size of slit. Now, every time you are to solve a problem in physics, in chemistry, make sure that you first write down that formula. You don't substitute before writing it down. You write it down because that gives you marks. So we write it down and then we substitute into it, like I've done here. So we know that theta is 15 degrees. So in place of theta, we write 15 degrees. M, we are told that this first dark band appears at that angle. Now, there is this word here, first. That tells us that part of the information given to us is that m is equal to 1 because it's the first dark band. So we'll say that m is 1 times lambda, which is what we're looking for, divided by a, which is the size of the slit, that is 2 by 10 to the power minus 6. Now quickly, let's work this out. We know that from this, lambda will be given by, we cross multiply. Like I said, let's make this a fraction as well by dividing by 1. So when we cross multiply, this will be 1 times lambda. So it will be lambda equals 2 times 10 to the power minus 6 cross multiplication times sine 15 degrees. So that will be the size of lambda. Let's quickly use a calculator to solve this problem or to work out the answer. Now, we have lambda equals 2 by 10 to minus 6 times sine of 15 degrees. And let's see what the answer is. Lambda is very, very small, and let me count how many zeros are here. Just after the comma is 1, 2, 3, 4, 5, 6, 7. So that will be 5,18. 5,18 by 10 to the power minus 6. Did I count 6? So we have that 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So 5,18 by 10 to the power minus 7. That is what lambda is. And remember, this is in meters. Wavelength measured in meters. Now let's look at another example. Here it's a question that says find the position of the first dark band. So we know what m is there. Formed on the screen when red light of wavelength 690 nanometers is passed through a slit of width. So we have that information, 6.0 micrometers. Compare this position with the, we have to compare this position with the first dark band when blue light is used. Now blue light is used in the next section where we need to compare. Let's write down again what is given to us. We have got to find the position, and the position is the angle theta. So we don't know where theta is. We know m, it's the first, so it's plus 1. First dark band. We also know the wavelength of red light is given to us, 690 nanometers, so it's 690 by 10 to the power minus 9 meters. Okay, I've just converted there. We are also told that A, the size of the slit, it's 6 micrometers, so 6.0 by 10 to the power minus 6 meters. We have all that information. So we need to calculate for theta. From the formula, we know that sine theta equals, like I said, you write the formula in full first, m times lambda divided by a, which is the size of the slit. So we're looking for sine theta. We're looking for theta actually. So sine theta, we begin to substitute now, M we are told is the first one, so it's 1 times the wavelength for red light. It's 690 by 10 to the power minus 9. And then the slit size, we divide by the slit size, that is 6.0 by 10 to the power minus 6. And then let's now find what sine theta is. And of course, we will need a calculator for this exercise. All right, so this is 1 times 690, it's that 690. So we will just say 690 to exponent minus 9 divided by 6.086 by 10 to the power minus 6, right? And we get that as 0.115. 0.115. That is sine theta. We have not as yet found sine theta. To find sine theta, or to actually find theta, this is sine theta, we need to find the sine inverse of 0.115. And again, we need a calculator for that. Now, sine inverse, we need to use the shift button. So we'll say shift sine inverse of 0.115. Okay? And then what will that be? We will see that the angle is 6.60. So theta, therefore, theta is 6.60 degrees. So that is the value of theta. But we need to compare this to when you are using a blue light. Now, for using the blue light, we would have, I'm not now going to write this formula in full. I have it there. Let me just quickly put the answers there. The first dark band, it's 1m times, now the wavelength of the blue light is 469. So 469 nanometers times 10 to the power minus 9 to convert, divided by the same size of the slit, because we're still using the same slit. So it's 6.0 by 10 to the power minus 6. Let's work out what that is going to be. 469 by 10 to the power minus 9 divided by 6 by 10 to the power minus 6. And that gives us the answer. So sine theta is 0.078. Now, theta equals sine inverse of 0.078. And again, we can quickly get that from the calculator. So we'll just say shift the second function, sine inverse of 0.078. And we find what the answer is. And it says the angle is going to be 4.47. So theta will be 4.47 degrees. Now, the question was that we need to compare this to that. Now, the position of the first dark band is higher for red light compared to blue light. So that's what we needed to see compared to blue light. Okay, so that answers that particular problem. And quickly as we close, other diffraction patterns can be looked at when we looking at double slit, not just single slit, and then maybe also looking at diffracting or diffraction gratings. Now we've come to the end of this session, and I hope you enjoyed it. Now it's time for me to say goodbye, keep well, And as you know, my name is Tinyiko Kosa. Enjoy it. Bye-bye.